Look up at the night sky on a clear evening. You see pinpricks of light, distant stars, entire galaxies so far away their light has traveled for millions, even billions of years to reach your eyes. It's a view that feels eternal, unchanging, but we now know that this is an illusion. The universe is not static. It is stretching, expanding, carrying those galaxies away from us in a grand cosmic dance that began with the Big Bang. For nearly a century, we've measured the rate of this expansion, a single, crucial number known as the Hubble Constant. It's the key to unlocking the universe's age, its fate, and its ultimate composition. But what if this fundamental number, this pillar of modern cosmology, is wrong? What if the very tools we use to measure our cosmos are telling us two conflicting, irreconcilable stories? This isn't just a small discrepancy. It is a full-blown crisis, a chasm in our understanding so deep and so puzzling that it has become the single most significant problem in all of modern science. This crisis has a name, the Hubble Tension. Imagine the most brilliant scientific minds on the planet, armed with the most powerful telescopes ever built, peering into the deepest voids of space. One group looks at the ancient afterglow of the Big Bang and calculates one very specific speed for the universe's expansion. Another group looks at nearby stars and galaxies, using them as cosmic mile markers, and arrives at a different, faster speed. These aren't just slightly different answers, they are stubbornly, definitively different, and this isn't a minor accounting error. This is a fundamental disagreement about the current state and the entire history of our universe. It suggests that something crucial is missing from our models, that a piece of the cosmic puzzle is either hidden from view or that we have fundamentally misunderstood a law of physics we thought was set in stone. This is the exciting mystery we are going to explore together. This single number, the Hubble Constant, is causing a monumental headache for astronomers worldwide, and the implications are staggering. It forces us to ask profound questions. Could there be new, unknown particles flooding the cosmos? Did the early universe behave in a way we never anticipated? Or is our entire conception of dark energy, the mysterious force driving the expansion, completely flawed? In this journey, we will dive deep into the heart of this mystery, breaking down 25 specific reasons why the Hubble tension is so incredibly perplexing. We will look at the conflicting data, the ingenious methods used to measure the immeasurable, and the thrilling, sometimes bewildering, theories that scientists are proposing to bridge this cosmic divide. This is a story about the frontiers of human knowledge, a puzzle that could very well rewrite the textbooks and redefine our place in the cosmos. To understand the depth of this problem, we need to start with the very tools that created it. And the first major reason the Hubble tension is so baffling is that it's a disagreement between our two most trusted cosmic measuring tapes. These aren't back-of-the-envelope calculations or tentative new techniques. These are the gold standards of cosmology, each refined over decades to an incredible degree of precision. Yet they point to two different realities. The first method acts as a local cosmic surveyor, taking measurements in our own cosmic neighborhood. This is known as the distance ladder, and it works in a beautifully straightforward way, much like how you might judge the distance to a car at night by the apparent brightness of its headlights. Astronomers use pulsating stars called Cepheid variables as their primary rung on this ladder. These stars have a wonderful property. The rate at they pulse is directly tied to their true intrinsic brightness. By measuring their pulse rate from Earth, scientists know exactly how bright they should be, and by comparing that to how dim they appear, they can calculate the precise distance to their host galaxy. From there, they use these Cepheids to calibrate even brighter cosmic flares, type Ia supernova. These supernovae are so brilliant and uniform in their peak brightness that they can be seen across vast cosmic distances, allowing us to measure how fast the space between us and those exploding stars is stretching. After painstakingly building this ladder step by step, This local measurement gives us a Hubble constant of about 73 kilometers per second per megaparsec. This means that for every additional megaparsec of distance, a staggering 3.26 million light-years, a galaxy is moving away from us 73 kilometers per second faster. Now let's journey back in time, almost to the very beginning of everything. The second gold standard method doesn't look at nearby stars at all. It looks at the oldest light in the universe. This is the cosmic microwave background, or CMB, the faint afterglow of the Big Bang itself, released when the universe was just a hot, dense plasma about 380,000 years old. The Planck satellite, a European Space Agency mission, mapped this relic light with exquisite detail, capturing tiny variations in temperature, hot and cold spots that are like a baby picture of the cosmos. By studying the precise patterns in this light, scientists can work backwards, applying our well-tested understanding of physics to calculate how the universe must have evolved from that infant state to what we see today. This includes calculating what the expansion rate should be right now. The result from this pristine early universe method is a Hubble constant of around 67.4, a figure that is significantly slower and completely at odds with the local measurement. The truly unsettling part is the incredible precision of both results. The error bars are so small that these two values do not overlap. They are definitively, irreconcilably different. It's as if you used two different, perfectly calibrated rulers to measure the same table and got two distinct answers that were both unequivocally correct according to their own standards. This isn't a case of one method being sloppy. It's a fundamental clash between the story of the universe's infancy and the story of its present day, and that is why this disagreement sits at the very core of the cosmological crisis. And that brings us to the second and perhaps more startling reason this tension is so profound: the sheer size of the gap. On the surface, a difference between 73 and 67 might not sound like much. It's the kind of minor variation you might shrug off in everyday life. But in the rarefied world of high-precision cosmology, this isn't a small rounding error, it's a chasm. To understand why, you need to think not in terms of the numbers themselves, but in terms of certainty. Scientists use a unit called sigma to measure how significant a finding is. A 1 or 2 sigma result might be a fluke, a bit of statistical noise that could easily disappear with more data. But as that sigma value grows, the probability that the result is a mere accident plummets spectacularly. The disagreement between the local and early universe measurements isn't a tentative 2 or 3 sigma issue. It's a monumental 5 to 6 sigma discrepancy. At this level of confidence, the chance that this conflict is a random mistake is less than 1 in a million. It's the same gold standard threshold used to announce the discovery of the Higgs boson particle. This isn't a suggestion that something might be wrong. It's a screaming, statistically undeniable declaration that something is wrong. Think of it like this. Imagine you have 2 of the most accurate atomic clocks ever built. They are marvels of engineering, so precise they wouldn't gain or lose a second over millions of years. Now you set them side by side and let them run. According to everything we know, they should tick in perfect, unwavering unison. But instead, you find that one of them consistently runs faster than the other, gaining several minutes every single day. That isn't a tiny, acceptable drift. That's a fundamental failure of your understanding of timekeeping itself. The 2 methods for measuring the Hubble constant are our cosmic clocks. The local distance ladder and the primordial CMB are both technological and theoretical masterpieces, refined to an almost unimaginable degree. They should be telling us the same time for the cosmos. The fact that they are so starkly out of sync tells us with overwhelming statistical force that our standard model of cosmology, the very foundation of how we understand the universe's evolution, is missing a crucial piece. This discrepancy is far too large to be explained away by blaming the instruments. the problem must lie deeper, woven into the fabric of the universe or our laws of physics in a way we have yet to comprehend. Now consider a third reason that adds another layer of bewilderment to this entire situation. You might assume that with better technology and more data, such a stark conflict would simply fade away. That's how science usually works. Initial disagreements get resolved as our tools improve and our view becomes clearer. But with the Hubble tension, the exact opposite is happening. Over the past decade, both camps, the local surveyors and the early universe observers, have been in a kind of scientific arms race, refining their techniques to an astonishing degree. On one side, the Hubble Space Telescope has been meticulously observing more Cepheid variable stars, painstakingly building a more robust cosmic distance ladder. At the same time, the Gaia spacecraft has been performing a galactic census, providing exquisitely precise measurements of the distances to the very stars used to calibrate this ladder, tightening the entire system. The result is a local measurement of the Hubble constant that is sharper and more confident than ever before. On the other side, the final data release from the Planck satellite delivered the most detailed map ever created of the cosmic microwave background, a snapshot of the infant universe with such clarity that cosmologists could extract its parameters with incredible certainty. The shocking outcome of all this progress is not a reconciliation. It's a deepening of the divide, as the uncertainty shrank on both sides, as the error bars tightened from fuzzy, wide margins into sharp, narrow lines. The two values did not gracefully slide toward each other. Instead, they have held their ground stubbornly, making the gap between them not just persistent, but statistically more significant and pronounced with every new data release. The better we can see, the more real the problem becomes. This isn't the story of a mistake being corrected. It's the story of a fundamental feature of the universe being revealed. The tension is not an artifact of noisy data. It is the data itself telling us that our standard cosmic model, for all its success, is incomplete. But perhaps the most unsettling aspect of this entire situation is the fourth reason the Hubble tension is so deeply troubling. It represents a direct and forceful challenge to the very foundation of modern cosmology, the lambda cold dark matter model, or lambdactum for short. Think of this model as the playbook for the entire universe. It's the set of rules and ingredients that we have used for decades to describe everything from the formation of the first galaxies to the large-scale cosmic web we see today. And until now, its predictive power has been nothing short of spectacular. The model is built on a few key pillars: that the universe is mostly made of a mysterious, invisible substance called dark matter, which provides the gravitational scaffolding for galaxies to form, and that it is dominated by an even more enigmatic force known as dark energy, symbolized by the Greek letter lambda, which is causing the expansion of the universe to accelerate. This lambdactum model, with its specific blend of ordinary matter, dark matter, and dark energy, has passed every major test we've thrown at it. It accurately predicted the patterns we see in the cosmic microwave background and successfully explained the distribution of galaxies across the void. It has been our most reliable guide to the cosmos. The Hubble tension, however, is like a crack appearing in the foundation of this entire theoretical structure. The Planck measurement of the cosmic microwave background is not a standalone number. It is a direct product of the lambdactum model. When scientists analyze the subtle patterns in that ancient light, they are essentially plugging those patterns into the lambdactum equations to derive what the Hubble constant must be today. The fact that this derived value clashes so violently with the direct, local measurement is a clear signal that the model used for the derivation might be flawed. It suggests that the universe, as it evolved from its hot, dense infancy to its current state, did not follow the precise script we have written for it in our lambdactum playbook. Something unexpected happened along the way, or something fundamental is missing from our list of ingredients. This isn't a minor adjustment, like tweaking a recipe by adding a pinch more salt. This is the equivalent of discovering you've been missing an entire major ingredient all along, one that alters the entire outcome. This forces physicists into an uncomfortable position. They must now seriously consider possibilities that were once on the fringes of cosmology. Perhaps dark energy isn't a constant force, as the standard model assumes, but a dynamic field that has changed its strength over the history of the universe. Maybe dark matter has properties we never anticipated, allowing it to interact with itself or with normal matter in strange new ways. Or there could be an entirely new type of relativistic particle, often referred to as dark radiation, that flooded the early cosmos and altered its expansion rate in a way our current models don't account for. Each of these ideas is a potential modification to the bedrock lambda model, and while they might solve the Hubble tension, they risk breaking the beautiful consistency the model has with all the other data we've collected. We are left with a profound scientific dilemma. Do we abandon our most successful cosmological framework, a theory that has explained so much, because of this one persistent discrepancy? Or do we trust the framework and assume there must be some hidden, as yet unknown systematic error in our measurements? The Hubble tension has placed cosmology at a crossroads, forcing a re-examination of our most basic assumptions about the nature of reality itself. Yet perhaps the most electrifying reason the Hubble tension captivates scientists and the public alike is what it potentially represents, a glaring signpost pointing toward entirely new physics. For decades, our understanding of the cosmos has been anchored by the standard model of particle physics and the lambda-cold dark matter model of cosmology. Together, they form a powerful, if incomplete, rule-book for the universe. But what if the Hubble tension is the universe's way of telling us that this rule-book needs a major revision? The discrepancy is so stark and so persistent that it cannot be easily dismissed, forcing us to consider that we might be on the verge of a breakthrough as monumental as the original discoveries of dark matter and dark energy. This isn't just about fixing a calculation. It's about potentially uncovering a fundamental aspect of reality that has, until now, been completely hidden from view. One of the most compelling ideas is that our understanding of dark energy is fundamentally flawed. In the standard cosmological model, dark energy is represented by Einstein's cosmological constant, a form of energy that permeates the vacuum of space and has a constant, unchanging strength throughout cosmic history. This constant force is what drives the accelerating expansion of the universe we observe today. But what if dark energy isn't constant at all? Imagine a universe where this mysterious repulsive force was stronger in the past or is slowly weakening over time. This concept, known as dynamical dark energy, could provide a neat solution to the Hubble tension. If dark energy was more potent in the universe's adolescent years, it would have given the expansion an extra push, causing the cosmos to evolve more quickly from its early state to its present-day size. This would mean that when we use the early universe's light, the cosmic microwave background, to predict the current expansion rate, our prediction would be too low because our model incorrectly assumed a constant, gentle push from dark energy. The faster local measurement would then be the correct one, reflecting a cosmos that has actually been expanding more vigorously than we thought. The implications of this are staggering, suggesting that the force dominating the fate of our universe is even more alien and complex than we imagined. Then there is the enigma of dark matter. We know it exists due to its profound gravitational influence, but we have never directly detected it, and its fundamental nature remains one of physics' greatest mysteries. The Hubble tension could be a clue that dark matter is not the simple, cold, and non-interacting substance we have assumed it to be. What if certain types of dark matter can decay or interact with itself? If a portion of the dark matter in the early universe transformed into other particles, it would have subtly altered the rate at which cosmic structures formed and the way space itself expanded. This kind of interaction isn't accounted for in our standard models, and its inclusion could tweak the predicted expansion history just enough to bridge the gap between the early and late universe measurements. It suggests that dark matter is not a monolithic, passive substance, but may have a rich and dynamic physics of its own. Beyond dark energy and dark matter, theorists are exploring the possibility of entirely new components to the cosmos. One leading candidate is the existence of what's known as dark radiation. This isn't radiation in the sense of light, but rather a hypothetical form of energy made up of elusive, fast-moving particles that barely interact with normal matter. In the first few moments after the Big Bang, the presence of such particles would have increased the total energy density of radiation, which in turn would have altered how quickly the primordial plasma rippled and oscillated. These oscillations are imprinted in the pattern of the cosmic microwave background, and if our models are missing this extra ingredient, our interpretation of that ancient light would be systematically off. Adding a dash of dark radiation to the cosmic recipe could reconcile the early universe prediction with the local measurement, effectively telling us that the universe in its infancy was a more energetic and complex place than our current theories allow. Each of these possibilities, dynamic dark energy, interacting dark matter, or dark radiation, opens a thrilling new window into the fundamental laws of nature. They are not minor adjustments, they are profound shifts in our cosmic paradigm. The Hubble tension, therefore, is far more than a technical disagreement between two sets of data. It is a catalyst. It is pushing cosmologists to question pillars of modern physics and to dream up entirely new theoretical landscapes. The excitement in the scientific community is palpable because this isn't a problem that can be solved by simply building a bigger telescope. It may require a revolution in our thinking, one that could ultimately reveal a deeper, more complete story of the universe and our place within it. While our standard cosmological model faces a monumental challenge, it's crucial to understand that the local measurement of the Hubble constant is not a single, simple observation. It is a meticulous, multi-step construction project known as the cosmic distance ladder, and its intricate nature is the sixth reason the Hubble tension is so perplexing. Think of trying to measure the height of a skyscraper with a single, tiny ruler. It would be impossible. Instead, you might use the ruler to measure the height of one step, then use that step to calibrate the length of your stride, then use your stride to pace out the length of the lobby, and finally use that to estimate the building's full height. Astronomers face a similar problem, but on a cosmic scale. They must start with direct geometric measurements in our own galactic neighborhood and then carefully leapfrog outward, using each newly calibrated rung to reach the next. The entire process is a chain of inference, and as with any chain, its overall strength is only as good as its weakest link. The first and most fundamental rung on this ladder is based on pure geometry, a method called stellar parallax. It's the same effect you experience when you hold a finger in front of your face and close one eye, then the other. Your finger appears to shift position against the background. As Earth orbits the Sun, astronomers can observe the same subtle shift in the positions of the nearest stars against the more distant celestial backdrop. By meticulously measuring this tiny angular wiggle over 6 months and knowing the diameter of Earth's orbit, they can use trigonometry to calculate the precise distance to these stars with extraordinary accuracy. This is the gold standard, the foundation upon which everything else is built. Missions like the European Space Agency's Gaia spacecraft have revolutionized this first step, providing parallax measurements for over 1 billion stars and creating an ultra-precise three-dimensional map of our cosmic backyard. With this secure foundation, astronomers can now move to the next critical rung, Cepheid variable stars. These aren't just any stars, they are cosmic lighthouses with a remarkably reliable pulse. Discovered by Henrietta Swan Leavitt over a century ago, Cepheids have a direct relationship between their intrinsic brightness and their pulsation period. A Cepheids that pulses slowly is inherently much brighter than one that pulses rapidly. This period luminosity relationship is the master key. By using parallax to measure the exact distance to a few nearby Cepheids, astronomers lock in their true intrinsic brightness. Then, when they find a Cepheid in a more distant galaxy, they simply measure its pulse rate. They instantly know how brilliant it truly is, and by comparing that known brilliance to its apparent dimmed brightness as seen from Earth, they can calculate its distance with high confidence. Cepheids become the first major leap, allowing us to reach out to galaxies millions of light-years away. But even the brilliant light of Cepheids eventually fades from view at extreme distances. To probe the expansion of the universe itself, we need the universe's most powerful flashbulbs, type Ia supernova. These spectacular stellar explosions occur in binary star systems where a dense white dwarf star steals material from its companion until it reaches a critical mass and detonates. Because this critical mass is always the same, the peak brightness of these supernovae is incredibly uniform, making them what astronomers call standard candles. They can outshine entire galaxies and be seen across billions of light-years. Here's where the ladder is completed. Astronomers use Cepheid variables in galaxies that are relatively close to calibrate the exact peak brightness of any type Ia supernova that happen to occur in those same galaxies. Once this calibration is done, they can find a type Ia supernova in a galaxy far, far away, measure its observed peak brightness, and immediately know its distance. By then measuring the redshift of that host galaxy, how much its light is stretched by the expansion of the universe, they can directly calculate how fast the cosmos is expanding at that distance. This entire process is a masterpiece of scientific deduction, but its multi-step nature is also its greatest vulnerability. The sixth reason this tension is so troubling lies in the potential for tiny, hidden errors to creep in. Imagine a carpenter building a ladder where every rung is placed based on the measurement of the rung below it. If the first rung is even a millimeter too high, that error might be small. But by the time you reach the 10th rung, that millimeter has compounded into a centimeter of error, and by the 100th rung, the entire structure is unstable. In cosmology, a minuscule systematic error, a subtle miscalibration of a Cepheid's true brightness, or an unaccounted-for effect of interstellar dust dimming the light of a supernova, at any step of the ladder can propagate upward, skewing the final value of the Hubble constant. This is the constant, nagging worry for the teams doing this painstaking work. They are not just taking a single measurement, they are managing a chain of custody for cosmic data, where any break can lead to a misleading result. This inherent vulnerability is why other astronomers scrutinize every step so intensely, searching for that one hidden flaw that could resolve the tension. Yet, despite decades of such scrutiny, the local measurement has only become more robust, deepening the mystery rather than solving it. While the cosmic distance ladder builds its case step by step from our local cosmic neighborhood, the early universe measurement takes a radically different approach, and this leads us directly to the seventh, and perhaps most philosophically profound, reason the Hubble tension is so deeply puzzling. The Planck satellite's measurement of the Hubble constant is not a direct observation in any ordinary sense. We cannot simply point a telescope at the universe today and read off a value of 67.4. Instead, what Planck provides is a pristine, frozen-in-time snapshot of the cosmos, as it was just 380,000 years after the Big Bang. This snapshot, the cosmic microwave background, is a map of tiny temperature fluctuations, a cosmic fingerprint of the initial conditions of the universe. The value for today's expansion rate is not measured. It is inferred through a complex computational process that leans entirely on the theoretical framework of the lambda cold dark matter model. Think of it like a detective trying to determine the current location of a suspect. The detective doesn't have a live tracker. Instead, they have a single, clear photograph of the suspect leaving the scene of the crime, getting into a specific car and driving away down a known highway. To figure out where the suspect is now, the detective must use a model. This model includes the car's possible speed, the condition of the roads, the traffic laws, and the likelihood of the suspect making certain turns or stops. If the detective's model is perfect, they will predict the suspect's current location with pinpoint accuracy. But if the model is flawed, if, for instance, the detective doesn't know the suspect switched to a faster car or that a new highway was built, then the prediction will be wrong, no matter how clear the initial photograph was. In cosmology, the lambda cold dark matter model is that set of rules for the universe. It tells us how gravity will pull matter together into galaxies and clusters, how dark energy will push space apart, and how radiation and matter interacted in the early plasma. When scientists analyze the patterns in the cosmic microwave background, they are essentially feeding this baby picture of the universe into the lambda-quantum supercomputer and asking it to run the simulation forward 13.8 billion years. The output of that simulation is a prediction for what the universe should look like today, including a very specific value for the Hubble constant. The stunning and consistent result from this process is a value around 67.4. The crucial thing to understand is that this number is a direct consequence of the model's assumptions. It is the answer you must get if the lambda-quantum model is the complete and accurate story of the cosmos. This is why the Hubble tension strikes at the very heart of theoretical cosmology. The local measurement, the direct observation of the universe's current expansion, is like independently finding the suspect in a location that doesn't match the detective's prediction. The disagreement is not necessarily about the quality of the initial evidence. Both the CMB map and the local distance ladder are considered masterpieces of observational science. The conflict is about the rules of the journey. The fact that the model's prediction and the direct observation disagree so strongly implies that the lambda-quantum model, for all its monumental success, is an incomplete guide to the universe's evolution. Somewhere between that ancient afterglow and the present day, the cosmos behaved in a way that our standard playbook does not account for. The implications of this are staggering. It means that the Hubble tension is not merely a dispute about a number, it is a potential window into physics beyond our current standard model. Perhaps dark energy evolved, growing stronger or weaker over cosmic time. Maybe dark matter possesses a subtle complexity, interacting with itself or decaying in a way that subtly alters the expansion history. Or perhaps entirely new particles or forces were at play in the early universe, leaving a faint but decisive imprint on its growth. Each of these possibilities would represent a fundamental rewrite of a chapter in our cosmological story. The tension, therefore, is the universe giving us a vital clue. It is telling us that if we want to understand our present-day cosmos, we must first go back and reread the entire story of its life, because the ending we are observing today does not match the one predicted from its beginning. This growing confidence in the local measurement brings us to the eighth and critically important reason the Hubble tension is so confounding. It's not just one team's word against another's. The high value for the Hubble constant isn't the product of a single telescope or a solitary group of researchers who might have a unique blind spot. Instead, multiple independent teams, often using different types of stars and slightly different methodologies, have been converging on the same unsettling answer. This independent verification makes it exponentially more difficult to dismiss the local measurement as a fluke or a systematic error, forcing the scientific community to take the discrepancy with the early universe with the utmost seriousness. The most prominent of these efforts is the SH0 team, an acronym that stands for supernova H0 for the equation of state of dark energy. Led by Nobel laureate Adam Rees, this group has spent over a decade using the Hubble Space Telescope with meticulous precision, refining the cosmic distance ladder with Cepheid variables as their primary stepping stone. Their work is the gold standard, a painstaking multi-year campaign to observe these pulsing stars in galaxy after galaxy, slowly building an unassailable case for a Hubble constant around 73. But what if the entire Cepheid method has some hidden, universal bias that everyone has missed? To rule out that terrifying possibility, other groups have set out to build their own ladders, using completely different stars for the crucial middle rungs. This is where the Carnegie-Chicago Hubble program comes in. This independent collaboration decided to bypass Cepheid variables entirely and instead use a different class of stars known as red giants. Specifically, they focus on the point in a red giant's life when it undergoes a dramatic and predictable change called the tip of the red giant branch, or TRGB. At this precise moment, these stars all reach nearly the same peak intrinsic brightness. This makes them another fantastic standard candle, a powerful alternative to Cepheids. The Carnegie team meticulously observed these red giant stars in the same galaxies that host Type Ia supernova, building a parallel cosmic distance ladder from the ground up. The stunning result, their final value for the Hubble constant, was not a comfortable 68 or a compromising 70. It landed squarely in the same high-value territory as the SH0ES team, strongly supporting a faster expanding universe. The power of this independent agreement cannot be overstated. It's the scientific equivalent of having two separate detective agencies, using different investigative techniques and different informants, both identifying the same suspect for a crime. If both agencies point to the same person, your confidence in their conclusion skyrockets. In cosmology, the convergence of the SH0ES and Carnegie-Chicago results creates a formidable bulwark for the local measurement. It demonstrates that the high Hubble constant is robust. It doesn't depend on the idiosyncrasies of Cepheid variables or the specific analysis choices of one team. This cross-validation deepens the mystery profoundly because it systematically eliminates a whole class of potential excuses. We can no longer comfortably suggest that the entire local measurement is wrong because of some error unique to a single method. The problem must lie elsewhere, in the physics that connects the early universe to the present day. But the story doesn't end with the cosmic microwave background, and this brings us to the ninth and perhaps most convincing reason the Hubble tension is so hard to dismiss. The lower value for the Hubble constant isn't just coming from one single, albeit powerful, source like the Planck satellite. It finds strong, independent support from other entirely different probes of the early universe, creating a chorus of corroborating evidence that makes the disagreement with the local measurement even more stark and significant. One of the most powerful of these other methods involves studying the large-scale structure of the universe itself through what are known as baryon acoustic oscillations, or BAO for short. To understand BAO, we need to journey back to the universe's first few 100,000 years. At that time, the cosmos was a seething, hot plasma, a dense soup of particles and light. In this primordial fluid, gravity was trying to pull matter together into clumps, while the immense pressure of radiation was trying to push it apart. This tug-of-war created powerful sound waves, spherical pressure waves, that rippled outward through the plasma at a significant fraction of the speed of light. Then, when the universe cooled enough for atoms to form about 380,000 years after the Big Bang, a dramatic change occurred. The plasma cleared, the light was set free as the cosmic microwave background, and the particles that made up ordinary matter, known as baryons, suddenly found themselves stuck in place. Those rippling sound waves were instantly frozen in time, leaving a distinct, fossilized imprint on the distribution of matter. This imprint is the baryon acoustic oscillation. It manifests as a preferred scale in the universe, a specific distance of about 500 million light-years that you can detect by looking at how galaxies are clustered across the cosmos. When astronomers create massive three-dimensional maps of millions of galaxies, like those from the Sloan Digital Sky Survey, they don't see galaxies scattered randomly. They find that galaxies are slightly more likely to be separated from each other by this specific frozen sound wave scale than by any other distance. It's as if the universe has a built-in ruler, a standard measuring stick of a known physical length. By measuring the apparent angular size of this ruler on the sky at different cosmic epochs, astronomers can trace how the expansion of the universe has stretched this ruler over time. This provides a direct, clean measurement of the universe's expansion history, all the way from the early universe to the present day. And when this BAO data is combined with other constraints, particularly from the theory of Big Bang nucleosynthesis, which accurately predicts the abundance of light elements like hydrogen and helium created in the universe's first few minutes, the result consistently points toward a lower Hubble constant, perfectly in line with the value derived from the cosmic microwave background. This independent agreement is absolutely crucial to the entire puzzle. It means the tension isn't a simple two-way argument between the Planck satellite and the Hubble Space Telescope. It's a fundamental clash between two different eras of cosmic history, each with multiple independent witnesses. On one side, you have the local universe with its Cepheid variables, its red giants, and its supernova, all telling a consistent story of a faster expansion. On the other side, you have the early universe with its relic light from the CMB and its fossilized sound waves in the BAO, both telling a consistent and contradictory story of a slower expansion. This multi-pronged reinforcement on both sides of the divide solidifies the conflict. It systematically eliminates the possibility that the entire problem is just a glitch in the Planck data or a peculiarity of how we interpret the cosmic microwave background. The early universe methods are singing in harmony, and the local universe methods are singing in harmony, but they are singing two completely different songs about the current state of the cosmos. This consistency across disparate early universe probes transforms the Hubble tension from a curious discrepancy into an undeniable feature of our reality, a clear signal that our model of cosmic evolution is missing a crucial chapter. Now we arrive at a consequence of this cosmic conflict that is perhaps the most startling and philosophically jarring of all. The 10th reason the Hubble tension is so deeply troubling is that it creates a direct and embarrassing crisis in the very age of our universe. The Hubble constant is not just a measure of current speed, it is fundamentally a measure of cosmic time. Think of it as the universe's historical clock. If you rewind the expansion of the cosmos like playing a movie in reverse, all the galaxies rush back together. The Hubble constant tells you how quickly to run that rewind, and therefore how long it should take for everything to converge back to a single point, the moment of the Big Bang. A faster expansion rate, meaning a higher Hubble constant, implies the universe has been sprinting to reach its current vast size, suggesting a younger cosmos. Conversely, a slower expansion rate suggests a more leisurely, older universe. Here is where the numbers create a paradox that feels almost impossible to reconcile. The local measurement, with its high value of around 73, points to a universe that is approximately 12.5 billion years old. On the other hand, the early universe measurement, with its lower value of 67.4, gives us the familiar, comfortable age of about 13.8 billion years. At first glance, a difference of over a billion years might not seem catastrophic, but in cosmic terms, it is a chasm. This discrepancy becomes a full-blown crisis when we compare these ages to the oldest objects we can actually observe within the universe, stars that have been burning since nearly the dawn of time. The most famous of these ancient sentinels is a star whimsically nicknamed Methuselah, or more formally, HD 140,283. Located a mere 200 light-years away, this star is a galactic fossil, composed almost entirely of hydrogen and helium, with virtually none of the heavier elements that were forged in later generations of stars. Its chemical purity marks it as a relic from the very first stellar population, a star that formed when the universe was in its infancy. By meticulously studying its brightness and its stage of stellar evolution, astronomers have calculated its age. The result was stunning. Methuselah appears to be 14.5 billion years old, give or take about 800 million years. Now consider the implications. If the local Hubble constant is correct and the universe is only 12.5 billion years old, we are faced with an absurd and physical impossibility: a star that is 2 billion years older than the universe it resides in. It is the ultimate chronological paradox, like finding a birth certificate for a person who was born a decade before their own parents. Of course, the uncertainty in the star's age means its lower bound might just barely fit within the 13.8 billion year age from the early universe measurement, but it remains precariously close to the edge. This stellar age conflict is not an isolated case either. Globular clusters, dense, spherical swarms of hundreds of thousands of the oldest stars in our galaxy, also present a challenge. Many of these clusters have estimated ages very close to 13 billion years. If the universe itself is only 12.5 billion years old, there would have been virtually no time at all for the first galaxies to assemble, for the first clouds of gas to collapse, and for these magnificent star clusters to form and ignite. The cosmic timeline would be impossibly compressed. This creates a direct and profound challenge to our most basic understanding of the cosmic timeline. We have three different clocks, all ticking to different rhythms: the clock of the local expansion, the clock of the primordial afterglow, and the clock of the oldest stars. For our model of the universe to be consistent, these clocks must tell the same time. The fact that they do not is a glaring sign that something is fundamentally wrong. Either our method for dating the stars contains a hidden, significant error, which seems increasingly unlikely given our sophisticated stellar evolution models, or the universe's expansion history is not what we think it is. The Hubble tension, therefore, is not an abstract mathematical disagreement. It is a dispute about the very history of existence, forcing us to confront the possibility that the universe might be younger than its oldest inhabitants, a logical absurdity that demands a revolutionary solution. And this leads us directly to the 11th critical piece of the puzzle, a potential hidden gremlin in the local measurement that could, in theory, resolve the entire crisis: the pervasive, confounding role of cosmic dust. When we look out at the universe, our view is not perfectly clear. The vast spaces between stars are not entirely empty. They are filled with tiny, microscopic grains of silicate and carbon, a fine, mist-like material astronomers call interstellar dust. This dust doesn't just block light, it selectively scatters and absorbs it. Shorter, bluer wavelengths of light are more easily scattered away, while longer, redder wavelengths tend to pass through more readily. The result is that starlight passing through a dust cloud arrives at our telescopes both dimmer and redder than when it started its journey. This dual effect, dimming and reddening, is known as extinction, and for astronomers using stars as standard candles, it is a constant and formidable challenge. To understand why this is so critical, let's return to our cosmic distance ladder. The entire process hinges on knowing the true, intrinsic brightness of a Cepheid variable or a type Ia supernova. We observe how dim it appears from Earth, and from that we calculate its distance. But what if the star isn't just distant? What if it's also being dimmed by an unknown veil of dust along our line of sight? If we fail to correctly account for this dust extinction, we would mistakenly interpret the dimming as being entirely due to greater distance. We would conclude the star is farther away than it actually is. Now apply this logic to the final rung of the ladder. If we systematically overestimate the distances to the galaxies hosting our calibrating supernova, we would then be calibrating those supernova to be intrinsically fainter than they truly are. When we then use these incorrectly calibrated supernova to measure even more distant galaxies, we would again overestimate their distances. The final, catastrophic outcome of this chain of errors would be a systematic overestimation of the Hubble constant. The expansion rate would appear faster than it truly is, potentially creating the very tension we observe. This makes dust a prime suspect in the investigation. Perhaps the entire local measurement is skewed not by new physics, but by an old, familiar foe we haven't fully conquered. The teams behind these measurements are, of course, acutely aware of this danger. They invest immense effort in modeling and correcting for dust extinction. They observe their Cepheid stars at multiple wavelengths from the blue to the infrared because dust affects different colors of light in predictable ways. By comparing the star's color to its expected color, they can estimate the amount of reddening and thus correct for the dimming. It's a sophisticated and necessary correction. The billion-dollar question, however, is whether our current models of interstellar dust are sufficiently sophisticated to capture its full complexity. This is where a heated and ongoing debate lies. Some scientists argue that the dust in other galaxies might be different from the dust in our own Milky Way. What if the dust grains are systematically larger or have a different composition? Larger grains would not redden the light as effectively while still dimming it significantly. If this type of gray dust is common in the galaxies we use for our calibration, then our standard color-based corrections would fail. We would see a star that is dim but not particularly red, and we would incorrectly assume all the dimming is from distance. This would directly lead to the overestimation we fear. Other researchers propose that the dust might not be evenly distributed, but could exist in complex, clumpy structures that create a patchy extinction which is devilishly difficult to model accurately across an entire galaxy. The SH0ES team and others have run exhaustive tests on this very issue. They have analyzed their Cepheids in the infrared, where the effects of dust are minimized, and they still find a consistently high value for the Hubble constant. This is a powerful argument against dust being the sole culprit. If dust were the primary driver of the tension, its influence should vanish or greatly diminish when we look in the infrared. The fact that the discrepancy persists even in these longer wavelengths suggests that while dust is a complicating factor, it is unlikely to be the magic bullet that solves the Hubble tension. Yet the debate is not fully settled. The possibility remains that some novel, unforeseen property of interstellar dust or a subtle error in how we model its distribution could be contributing to the problem. It represents the constant, humbling challenge of observational astronomy. We are always looking through a partially dirty window, and we must be absolutely certain we know how to clean the glass before we can trust what we see on the other side. Now, we must shine a spotlight on the very heart of the local measurement, on the stars that carry the weight of the entire cosmic distance ladder on their luminous shoulders. This brings us to the 12th and profoundly intricate reason for the Hubble tension, the enduring mystery surrounding the calibration of Cepheid variable stars. These are not just any stars, they are the foundational rung, the trusted intermediaries that allow us to leap from our local galactic neighborhood out into the vast cosmic ocean. Their reliability is paramount, and the very fact that their inherent properties are now a subject of intense scrutiny shows just how deep this cosmological crisis runs. The power of Cepheids lies in their famous period luminosity relationship, a discovery that revolutionized astronomy. Simply put, a Cepheid that pulses slowly with a long period is intrinsically much brighter than one that pulses rapidly. By measuring the rhythm of its beat from Earth, an astronomer can know its true powerhouse wattage. The difference between that known brilliance and its faint, twinkling appearance in our sky reveals its distance. It's an elegant and powerful method, but it rests on one critical assumption, that all Cepheids everywhere obey the exact same rule. What if that's not entirely true? What if a Cepheid's true brightness is influenced by more than just its pulse? This is where the complex issue of metallicity enters the stage. In astronomy, metals refer to any element heavier than hydrogen and helium. The first stars in the universe were composed almost purely of these two primitive elements, But as generations of stars lived and died in spectacular supernova, they forged heavier elements like carbon, oxygen, and iron, seeding the cosmos with this stellar ash. A star's metallicity is a measure of how much of this ash it contains. A Cepheid born in an ancient, metal-poor galaxy will have a different chemical composition than one born more recently in a metal-rich galaxy like our own Milky Way. The multi-billion-dollar question is, does this difference in chemistry affect the star's internal physics and, crucially, its intrinsic brightness? Theoretical models suggest it very well could. The opacity of a star's outer layers, how easily light can pass through, is heavily influenced by its metal content. Higher metallicity can make the gas more opaque, trapping energy and potentially altering how the star pulsates and how much light it ultimately emits. If metal-rich Cepheids are systematically dimmer than our calibration expects, or if metal-poor ones are brighter, the entire distance ladder would be thrown off. When we observe a Cepheid in a distant galaxy, we measure its pulse and assign it a brightness based on Cepheids we've calibrated nearby. But if that distant Cepheid has a different metallicity, our assigned brightness would be wrong, and so would the distance we calculate. A chain of such errors could systematically bias the entire local measurement of the Hubble constant. To solve this, we need to nail down the calibration of nearby Cepheids with unshakable precision. This is where the European Space Agency's Gaia spacecraft was supposed to be the hero of the story. Gaia's mission is to perform stellar parallax on an unprecedented scale, creating a fantastically precise three-dimensional map of over 1 billion stars in our galaxy, including the very Cepheids we use as our primary standard. With Gaia's data, astronomers hope to measure the distances to these local Cepheids with near absolute certainty, locking in their period luminosity relationship and eliminating any lingering doubts. The results, however, have been anything but calming. Instead of cleanly resolving the tension, the incorporation of Gaia's early data releases sometimes made the situation more confusing. Different analyzers, using slightly different methods to handle Gaia's incredibly precise but complex data, have produced a swirl of conflicting recalibrations. In some cases, the new Gaia-based distances to Cepheids have actually increased the value of the Hubble constant, widening the gap with the early universe measurement rather than closing it. Other careful studies have found a smaller but still persistent tension. It's as if we were given the most accurate ruler in the world, but when we used it to check our foundation, we found that the foundation itself was slightly different than we thought, and not in a way that fixes the larger problem. This failure of a definitive resolution is in itself a powerful and troubling result. It tells us that the problem likely does not lie in a simple, gross error in the basic distance to our local Cepheids. The tension has survived our best attempt to kill it with superior data. This forces astronomers to consider even more subtle and pernicious possibilities. Perhaps the issue isn't just with the Cepheids themselves, but with the next step in the ladder, the Type Ia supernova they are used to calibrate. Or, more excitingly, it strengthens the case that the issue isn't with the ladder at all, but with the fabric of the universe the ladder is measuring. The steadfast nature of Cepheids, even under the intense scrutiny of Gaia, suggests that the cosmic clock is truly ticking at a different rate than our best models of the early universe predict. This brings us to a truly profound question at the heart of the local measurement. Are our ultimate cosmic beacons, the Type Ia supernova, truly as perfect as we have believed? This is the 13th reason the Hubble tension is so perplexing, as it forces us to scrutinize the second key rung of the cosmic distance ladder. For decades, these stellar explosions have been celebrated as the gold standard of standard candles. The underlying physics seems beautifully simple. A white dwarf star in a binary system accretes matter from its companion until it reaches a very specific critical mass limit, known as the Chandrasekhar limit. At this precise threshold, the pressure and temperature in the star's core become so extreme that it triggers a runaway thermonuclear explosion. Because this detonation always happens at the same mass, the resulting flash of light has been considered remarkably uniform in its peak intrinsic brightness. This consistency is what allows astronomers to use them across billions of light years. See how bright it appears, and you know exactly how far away it must be. However, as our observational capabilities have sharpened, a more nuanced and complex picture has begun to emerge. It turns out that Type Ia supernova might not all be identical twins. Instead, they could be more like siblings from a large family, sharing a strong family resemblance but with subtle yet important individual differences. Astronomers are now identifying potential subclasses of these supernovae. Some appear to be brighter or dimmer than the canonical standard, and some may even originate from a different physical scenario, such as the collision and merger of two white dwarfs, which might not always produce an explosion of exactly the same luminosity. If these variations exist and we are not correctly categorizing and calibrating for them, we are introducing a hidden source of error into the most crucial part of our cosmic measuring tape. The potential complications don't stop there. The environment in which a white dwarf lives and dies may also leave an imprint on its final, spectacular demise. Consider the age and chemical composition, the metallicity of the host galaxy. A supernova that ignites in an ancient, metal-poor galaxy, one that formed its stars long ago from primitive hydrogen and helium, might behave differently than one that explodes in a younger, metal-rich galaxy like our own Milky Way. The progenitor star's metallicity could influence the exact composition of the white dwarf, potentially altering the nuclear physics of the explosion and thus its peak brightness. Similarly, the overall age of the stellar population might affect the typical mass or separation of the binary systems that produce these supernovae. If supernovae in older galaxies are systematically even a few % fainter or brighter than those in younger galaxies, and we treat them all as identical, our distance measurements to those far-off galaxies will contain a subtle but cumulative bias. This environmental dependency is not just theoretical speculation. Observational studies have begun to find tantalizing and somewhat troubling correlations. Some analyses suggest that the supernova used to calibrate the final rung of the distance ladder, those in the same galaxies where we have Cepheid variables, might have different average properties than the supernova used to probe the expansion in the more distant universe. If this is true, then the calibration transfer from the local Cepheids to the distant supernova is imperfect. We would be, in effect, using a slightly mismatched set of rules. A miscalibration of just a few % in the intrinsic brightness of these cosmic lighthouses would be more than enough to account for the entire discrepancy we see in the Hubble constant. The local measurement's high value could simply be an artifact of us assuming these standard candles are brighter or dimmer than they truly are on average. The teams behind the Hubble constant measurements are, of course, acutely aware of this challenge. They perform exhaustive checks, meticulously analyzing the light curves and spectra of hundreds of supernovae, searching for any systematic trends linked to galaxy type or metallicity. They apply complex corrections to try to standardize the peak brightness, a process astronomers call standardizing the candle. Yet, the possibility remains that our standardization techniques are not yet perfect, that a residual, unaccounted-for effect is still woven into the data. This represents a humbling reminder of the complexity of the cosmos. What we initially perceived as a simple, perfect standard might, upon closer inspection, be a more diverse and context-dependent phenomenon. The search for the source of the Hubble tension, therefore, is also a drive to understand the final moments of stars in exquisite detail, because our grasp of the largest scales of the universe depends entirely on our precision in measuring these brilliant, individual flashes in the dark. But what if the answer to this cosmic riddle isn't hidden in the fundamental laws of physics, but is instead a consequence of our own cosmic address? This brings us to a fascinating and distinctly astrophysical possibility. The 14th reason the Hubble tension is so puzzling, the concept that we might be living inside a cosmic void. Imagine for a moment that our Milky Way galaxy and all the nearby galaxies we use to build our local distance ladder are not in an average, representative part of the universe. Instead, picture us residing in a vast, bubble-like region of space that is significantly emptier than the cosmic average, a local void. In such an underdense region, the gravitational landscape would be profoundly different. The relentless pull of gravity from normal matter and dark matter is what acts as a brake on the universe's expansion. In a place teeming with galaxies and clusters, this gravitational tug-of-war is fierce, slowing the expansion down. But in a giant void where matter is scarce, the brakes are much weaker. Here, the repulsive force of dark energy would meet less resistance, allowing space within the void to stretch at a faster rate than the universe overall. If this scenario is true, it would elegantly reframe the entire conflict. Our local measurement of the Hubble constant, giving us a value of 73, would be perfectly accurate, but only for our own peculiar, fast-expanding neighborhood. It would be a local speed limit, not a global one. The early universe measurement from the cosmic microwave background, however, provides a value that reflects the average expansion rate across the entire cosmos. The tension, then, would not be a sign of new physics, but simply a cosmic sampling error. We would be like a weather station placed in an unusually dry desert, correctly reporting a drought while the rest of the planet experiences normal rainfall. Our instruments are working flawlessly. We're just in a strange place that doesn't represent the whole. The plausibility of this idea hinges on the large-scale structure of the universe, which is anything but smooth. We know from galaxy surveys that matter is distributed in a vast cosmic web, an intricate architecture of dense filaments, massive clusters, and enormous, empty voids that can stretch for hundreds of millions of light years. Our local galactic group is part of what's known as the Laniakea supercluster, a staggering collection of over 100,000 galaxies. But even within such a massive structure, there can be significant variations in density. Evidence for a local underdensity has been mounting for years. Surveys mapping the galaxies around us have repeatedly suggested that we reside in a region, often called the local hole or KBC void, that is up to 40 or 50% emptier than the cosmic average, extending for perhaps 1 billion light years. This isn't a perfect vacuum, of course, but a relative scarcity of galaxies and clusters compared to other parts of the universe. The implications for our measurements are direct and significant. When we use Type Ia supernova to gauge the expansion rate, we are measuring how much the space between us and those exploding stars has stretched. If both we and the supernova reside inside the same local void, that stretch is influenced by the void's faster internal expansion. Our measurements would naturally yield a higher value. The early universe methods, in contrast, look at the entire sky, averaging over all directions and all densities, and thus give us the true global average. This void hypothesis is compelling because it is a simpler, more conventional explanation that doesn't require rewriting the laws of physics. It relies on known gravitational dynamics and the observed lumpiness of the cosmos. It suggests that the lambda cold dark matter model might be perfectly correct on a global scale, and that the Hubble tension is merely an artifact of our particular location in its grand, uneven tapestry. However, like every potential solution in this mystery, the local void idea faces its own formidable challenges. The primary issue is one of size and significance. For a void to cause the observed discrepancy in the Hubble constant, it would need to be exceptionally large and profound. Some calculations suggest we would need to be at the center of a void hundreds of millions of light years across with a density as much as 50% lower than average. While evidence for an underdensity exists, whether it is substantial enough to fully account for the 5 to 6 sigma tension is a matter of intense debate. Many cosmologists argue that such a gigantic and deep void would be extremely rare within the standard cosmological model. We would be fantastically unlikely to find ourselves in such a special place. Furthermore, such a vast underdensity should leave other imprints on the cosmos, such as a distinct signature in the motion of our galaxy relative to the cosmic microwave background, a phenomenon known as the kinematic dipole. While some studies claim to see hints of this, the evidence is not yet conclusive. This leaves us with a classic scientific standoff. Is the universe trying to tell us something profound and fundamental about dark energy or particle physics? Or are we simply cosmic provincials, living in a backwater region whose unusual expansion rate is fooling us into thinking the entire universe is behaving strangely? The void hypothesis offers a way to preserve our established models, but at the cost of placing us in a remarkably special location. The new physics hypotheses offer a more universal solution, but at the cost of overturning a brilliantly successful cosmological framework. This is the razor's edge on which modern cosmology now balances, and the ongoing hunt to map the cosmos in ever greater detail is our best hope for finding out which path leads to the truth. Building on the idea of our local cosmic environment, we arrive at a 15th and deeply fundamental reason the Hubble tension is so difficult to resolve. The universe's expansion is not the perfectly smooth, uniform flow we often imagine. Our foundational models of cosmology rest upon the cosmological principle, which states that on the largest scales, the universe is both homogeneous and isotropic, meaning it should look roughly the same in every direction and from every location. This principle is what allows us to treat the cosmos as a simple, expanding fabric. However, when we zoom in from those unimaginably vast scales, we find a reality that is far more textured and lumpy. We live in a cosmos sculpted by gravity, a place of extreme contrasts featuring immense, densely packed superclusters of galaxies and correspondingly vast, nearly empty voids. This cosmic unevenness means that the recession of galaxies, known as the Hubble flow, isn't a perfectly pristine river. It's a flow with ripples and eddies, and our position within this dynamic system might be subtly distorting our view. The pure expansion velocity of the universe, the signal we are trying to measure with the Hubble constant, can be contaminated by what astronomers call peculiar velocity. This is the local motion of a galaxy caused not by the expansion of space itself, but by the specific gravitational tugs of its massive neighbors. Our own Milky Way, along with the entire local group of galaxies, is not simply drifting apart with the Hubble flow. We are also sailing through space on our own unique trajectory, pushed and pulled by the gravitational forces of the most colossal structures in our vicinity. Think of it like trying to measure a steady, powerful ocean current while you're sitting in a small boat that is also being buffeted by strong, local winds. If you don't accurately account for the wind's effect on your boat, your measurement of the underlying current will be wrong. In cosmology, if we fail to perfectly disentangle our own peculiar velocity from the pure Hubble expansion, the local value we derive for the Hubble constant will be skewed. The most significant source of this gravitational pull is likely the most massive concentration of matter in our local universe, the Shapley supercluster. Located about 650 million light-years away in the direction of the Centaurus constellation, Shapley is a staggering gravitational behemoth, a dense knot of galaxy clusters containing many thousands of times the mass of our entire Milky Way. This immense concentration of matter creates a profound gravitational well, and everything in its vicinity, including our local group, feels its insistent pull. For decades, astronomers have known that our galaxy is moving at a considerable velocity relative to the cosmic microwave background. This motion, known as the CMB dipole, is partly due to the gravitational influence of nearby structures, and the Great Attractor, a region of overdensity including the Norma cluster, was once thought to be the primary culprit. We now understand that the Great Attractor itself is likely just being pulled toward the even more massive Shapley supercluster. This means our local motion is part of a vast cosmic river flowing toward this distant gravitational focal point. This motion has a direct and calculable impact on our measurements. When we observe a distant type Ia supernova to measure the expansion rate, we measure its redshift, the stretching of its light due to the expansion of space. But that measured redshift is a combination of two effects: the cosmological redshift from the universe's expansion and the Doppler shift from our own peculiar motion relative to that supernova. If we are moving toward a massive structure like Shapley, then in the opposite direction of the sky, we are effectively moving away from the galaxies we are observing. This adds an extra component of redshift to their light, making it appear as if they are receding from us faster than they truly are, purely due to our own motion. When we then plug these slightly inflated recession velocities into our calculation for the Hubble constant, we would naturally derive a value that is a little bit too high. The local wind is making the cosmic current appear swifter than it truly is on a global average. The critical question, then, is whether this effect is substantial enough to account for the entire discrepancy. Could the gravitational pull of the Shapley supercluster and other nearby overdensities be the hidden key that resolves the Hubble tension? Researchers have performed detailed calculations to model these flows and subtract their influence from the local data. The results are fascinating, but ultimately they seem to deepen the mystery rather than solve it. While our peculiar velocity does have a measurable effect, most studies conclude that it is too small to fully explain the stark 5 to 6 sigma gap between the local and early universe values. Correcting for these flows might adjust the local Hubble constant downward by a percentage point or two, but it doesn't bring it anywhere close to the value of 67 derived from the cosmic microwave background. The tension persists robust against this correction. This failure is in its own way as revealing as a success. It tells us that while our local cosmic environment is indeed complex and dynamic, its gravitational influences are not the silver bullet we might have hoped for. The deviation from a perfectly smooth Hubble flow is a real and important factor that astronomers must meticulously account for, but it appears to be just one piece of a much larger puzzle. The fact that the tension remains even after we filter out these local ripples strengthens the case that the problem is not merely an artifact of our specific location, but points toward a more universal issue. It suggests that the discordance is woven into the global expansion history of the cosmos itself, a fundamental mismatch between the story told by the universe's first light and the story unfolding in our contemporary cosmic neighborhood. Now, as we dig deeper into this cosmological conundrum, we encounter the 16th and perhaps most structurally daunting reason the Hubble tension is so confounding. The problem does not exist in isolation. The Hubble constant, h0, is not a lone variable that can be tweaked independently. It is deeply entangled with other fundamental parameters that describe the very fabric and contents of our universe. Think of the standard cosmological model as a perfectly tuned mobile, the kind you might hang over a baby's crib. Each piece is carefully balanced against the others. If you try to move just one piece in this case, forcing the Hubble constant to a higher value, the entire structure shudders, and other pieces are forced to shift in response to maintain balance, often creating new, unintended imbalances elsewhere. This intricate dance involves key players like the matter density of the universe, denoted by the symbol omega m. This parameter tells us the total amount of both ordinary matter and dark matter in the cosmos, governing how strongly gravity can pull on the expanding fabric of space. Another crucial character is sigma 8, which measures the amplitude of matter clustering. In simpler terms, sigma 8 describes how clumpy the universe is, how readily matter coalesced into the vast cosmic web of galaxies and clusters we observe today. The early universe data from the Planck satellite doesn't just give us a value for H0, it gives us a tightly constrained combination of H0, omega m, and sigma 8 that is perfectly consistent with the lambda cold dark matter model. This specific combination is what successfully predicts the intricate pattern of the cosmic microwave background. Here is the core of the problem. If we want to take the Planck CMB data and force it to be consistent with the higher local value of the Hubble constant, we cannot simply turn one dial. We must also adjust these other parameters. To accommodate a faster expanding universe, the model typically requires a lower overall matter density, omega m. With less matter providing gravitational braking, the universe can expand more quickly, bringing the early universe prediction up to match the local measurement. However, this adjustment sends ripples through the entire model. A lower matter density would, in turn, affect how readily structures form. This is where sigma 8 comes in. The Planck data prefers a specific level of cosmic clumpiness that matches the patterns imprinted in the ancient light. If we lower omega m to raise H0, we often find that the predicted sigma 8 also changes, moving out of alignment with what we actually observe in the late-time universe. This creates a cascade of new tensions. For example, one of the most powerful ways to measure the clumpiness of the modern universe is by counting galaxy clusters. These colossal structures, containing thousands of galaxies, are the most massive gravitationally bound objects in existence. Their abundance is exquisitely sensitive to the values of both omega m and sigma 8. If our modified model, tuned for a high H0, predicts a universe that is significantly more or less clumpy than what we actually see from galaxy cluster surveys, then we haven't solved the Hubble tension. We've merely traded it for a sigma 8 tension. It's like a doctor treating a patient's fever by giving a medicine that cures the fever but causes a severe rash. You've addressed one symptom only to create another, equally troubling one. This interconnectedness is what makes finding a simple, elegant solution so incredibly difficult. Any proposed fix, whether it's a new form of dark energy or a tweak to dark matter, must do more than just bridge the gap in the expansion rate. It must do so without breaking the beautiful consistency the Standard Model has with a whole host of other independent observations, from the large-scale distribution of galaxies to the gravitational lensing of light around massive objects. The Hubble tension, therefore, is not a single loose thread that we can pull without consequence. It is woven into the entire tapestry of modern cosmology, and tugging on it threatens to unravel the coherent picture we have spent decades carefully stitching together. This places theorists in a formidable bind, forcing them to propose solutions that are not just imaginative, but also remarkably precise in their ability to adjust multiple cosmic parameters in perfect, harmonious concert. Moving from the large-scale gravitational tugs of superclusters, we now dive into the realm of the incredibly small, where ghostly particles that barely interact with anything could hold a surprisingly powerful key to this cosmic puzzle. This brings us to the 17th reason the Hubble tension is so captivating: the potential role of neutrinos. These subatomic phantoms are produced in staggering numbers by nuclear reactions, from the heart of the Sun to the cataclysmic explosions of supernovae. Trillions of them are passing through your body every second, completely unnoticed, as they rarely bump into any other particles. For decades, our cosmological models have treated neutrinos as essentially massless, or at least possessing such a tiny, negligible mass that they barely influence the grand narrative of cosmic evolution. But what if that assumption is what's blinding us to the solution? The secret to the universe's expansion rate might be hidden in the subtle weight of these ghostly particles. The impact of neutrinos hinges on a critical transition in cosmic history. In the very early, hot, dense universe, particles like neutrinos were moving at nearly the speed of light. At these incredible speeds, their energy manifests in a way that acts like radiation, pushing the expansion of space outward. However, as the universe expanded and cooled, these particles slowed down. Once their velocity drops sufficiently, their behavior shifts from acting like radiation to acting like matter. This is a profound change. Radiation exerts an outward pressure that drives expansion, while matter, through its gravitational pull, acts as a brake trying to slow the expansion down. The precise moment when neutrinos made this transition from behaving like radiation to behaving like matter depends on one crucial property: their mass. Heavier neutrinos would have made this switch earlier in cosmic history. Now, let's connect this physics to the Hubble tension. The early universe measurement from the cosmic microwave background is exquisitely sensitive to the total amount of radiation present in that infant cosmos. If we introduce heavier neutrinos or an additional hypothetical type of neutrino, it alters this early energy budget. Imagine a scenario where neutrinos have a larger total mass than our current estimates. These heavier neutrinos would have transitioned from radiation-like to matter-like behavior sooner. This means that in the epoch just before the release of the CMB, there would have been slightly less radiation pressure pushing the universe apart than our standard models assume. With less outward push from radiation, the gravitational pull of matter would have gained a slightly stronger foothold, causing the primordial plasma to clump together a bit more readily. This subtle change in the clumping would be imprinted on the patterns of hot and cold spots in the cosmic microwave background. When scientists analyze the CMB data with the assumption of standard, lightweight neutrinos, they derive one value for the Hubble constant. But if they reanalyze that same data, allowing for the possibility of heavier neutrinos, the model can accommodate a higher expansion rate. It's a delicate recalibration of the early universe's physics that could allow the CMB-derived prediction to shift upward, closer to the value we measure locally. This possibility becomes even more intriguing when we consider a hypothetical particle known as a sterile neutrino. As the name implies, this would be an even more elusive cousin to the three known types of neutrinos. The crucial difference is that a sterile neutrino would not interact via the weak nuclear force at all. It would feel only gravity. Because of its aloof nature, it's incredibly difficult to detect directly. If such a particle exists, it would have been a significant component of the early universe's particle zoo. A sterile neutrino would effectively act as a form of dark radiation, adding extra energy density to the cosmos in its first few 100,000 years. This additional component would change how the sound waves in the primordial plasma rippled and oscillated, which in turn changes how we interpret the patterns in the CMB. By including sterile neutrinos in the model, cosmologists can, once again, find a fit to the CMB data that points to a higher Hubble constant, potentially bridging the gap with the local measurement. It's a compelling idea because it uses a known class of particles, albeit with unknown properties, to solve the problem without requiring a complete overhaul of our fundamental physics. However, like every potential solution in this saga, the neutrino hypothesis is caught in a web of constraints from other fields of physics. Particle physics experiments here on Earth, such as those studying the oscillations of neutrinos from nuclear reactors and particle accelerators, have placed their own limits on neutrino masses and the possible existence of a fourth, sterile type. So far, no experiment has provided definitive evidence for sterile neutrinos, and the allowed range for the masses of the three known types is quite narrow. This creates a classic tension between cosmology and particle physics. Cosmological data, when interpreted to solve the Hubble tension, seems to point toward neutrino properties that are just on the edge or even outside of what terrestrial experiments allow. This doesn't kill the idea, but it forces it into a very tight corner. Proponents must carefully navigate these competing constraints, searching for a specific mass or a specific type of sterile neutrino that can satisfy both the cosmic microwave background and the data from underground particle detectors. The ghostly neutrino, a particle we once thought was too insignificant to matter, has now found itself at the center of a cosmological storm, its elusive mass potentially holding the secret to why the universe's two most trusted clocks are stubbornly ticking at different rates. But perhaps one of the most elegant and widely discussed theoretical proposals to solve this crisis introduces a fascinating new character to the cosmic drama. And that is the 18th reason the Hubble tension is so captivating, the hypothesis of early dark energy. We are already familiar with the concept of dark energy as the mysterious force responsible for the universe's accelerating expansion today. The Standard Model treats this force as a constant, an unchanging presence symbolized by the cosmological constant, lambda. But what if dark energy wasn't always so steady? What if, in the universe's fiery youth, there was an extra, transient surge of this repulsive energy, a kind of cosmic booster rocket that fired only for a brief, critical moment in cosmic history? This is the essence of the early dark energy idea. It proposes that in the first few 100,000 years after the Big Bang, a significant additional form of dark energy permeated the cosmos, influencing its expansion in a way that our current models completely miss. To understand how this works, imagine the early universe as a pot of water coming to a boil. In our Standard Model, the heat, the energy density is provided by a predictable mix of radiation and matter. Now, imagine someone briefly turns up the burner, adding an intense, temporary burst of extra heat. The water would bubble more vigorously for a short time before settling back to its previous boil. Early dark energy acts like that temporary turn of the burner. This hypothetical energy field would have been significant only in the epoch immediately before the release of the cosmic microwave background, roughly between the universe's first few thousand years and its 380,000th birthday. During this window, this extra component would have contributed additional outward pressure, causing the young cosmos to expand just a little bit faster than our standard models calculate. Then, as the universe cooled and evolved, this early dark energy would have rapidly faded away, becoming utterly negligible by the time the first stars formed, leaving the later cosmic evolution to be dominated by the dark energy we observe today. This seemingly minor tweak to the early universe has a profound and direct impact on the Hubble tension. The Planck satellite's measurement is exquisitely sensitive to the conditions of the universe at the moment the CMB was released. Think of that moment as the starting line for a cosmic race. The CMB gives us a snapshot of the universe's size, temperature, and composition right as the starting pistol fires. Our Standard Model then uses the known physics of gravity, dark matter, and a constant dark energy to project how that race should proceed, predicting where the universe should be today, its current size and expansion rate. The problem is that prediction gives us a slower Hubble constant than we actually measure. Now, introduce early dark energy. By giving the universe an extra push right before the starting pistol, you effectively change the initial conditions. The universe at the moment of the CMB's release is ever so slightly larger than it would have been without this boost. Because it's a bit more stretched out from the very beginning, it takes less subsequent expansion to reach the vast size we see today. When cosmologists rerun the simulation with this revised starting point, the model can now perfectly match the intricate patterns seen in the CMB while simultaneously predicting a present-day expansion rate that is significantly higher, much closer to the 73 measured by the local distance ladder. It's a brilliant piece of theoretical jiu-jitsu, using a modification in the ancient past to solve a problem in the present. The beauty of this proposal is its surgical precision. It doesn't require us to throw out our successful understanding of late-time dark energy. The cosmological constant that drives the acceleration we see today can remain unchanged. Early dark energy is a separate, transient phenomenon that operates only in the primordial universe, tweaking the initial conditions that we feed into our models. This makes it an attractive solution because it fixes the Hubble tension without breaking the many other successful predictions of the lambda-cold dark matter model for the later cosmos. It's like discovering that a historical document you've been using had a misprinted date. Correct that one initial piece of data, and the entire subsequent narrative falls perfectly into place. Of course, such an elegant idea is not without its own challenges. This new energy component must be fine-tuned. It has to be strong enough to make a difference, but it must also decay away at exactly the right rate to avoid messing up other well-measured processes, such as the formation of the first light elements. Furthermore, it is a hypothetical field. We have no direct evidence for its existence yet. But as a targeted solution to one of cosmology's most stubborn problems, early dark energy stands as a testament to the creative power of scientists who are willing to reimagine the first moments of everything to explain the universe we live in now. As the debate intensifies, a powerful new class of measurement is emerging, one that promises to cut through the entire Gordian knot of the cosmic distance ladder and offer a completely independent verdict on the expansion rate. This is the 19th and perhaps most revolutionary reason the Hubble tension is so compelling: the urgent challenge of finding a truly independent anchor for our cosmic measurements. For decades, the entire local value of the Hubble constant has rested on the intricate, multi-step construction of the distance ladder, with all its potential vulnerabilities to dust, metallicity, and calibration uncertainties. What if we could bypass all of that? What if we could measure distances directly without relying on the perceived brightness of any star or galaxy? This is no longer a theoretical dream. It is the new frontier of multi-messenger astronomy, and it hinges on listening to the very ripples in spacetime itself. The breakthrough comes from gravitational waves, the cosmic vibrations predicted by Einstein and finally detected in 2015. When two incredibly dense objects like black holes or neutron stars spiral inward and collide, they shake the fabric of spacetime, sending out waves that travel across the universe at the speed of light. For our purposes, the most valuable of these cosmic crashes are the mergers of two neutron stars. Unlike merging black holes, which are generally invisible, a neutron star merger is a multi-sensory extravaganza. It unleashes a torrent of gravitational waves, but it also typically produces a brilliant flash of light across the electromagnetic spectrum, from gamma rays to visible light to radio waves. This combination is the key to a revolutionary new measuring technique, one that gives these events a magnificent name: standard sirens. The principle is beautifully direct and relies on pure geometry, much like stellar parallax but on a cosmic scale. The gravitational wave signal we detect here on Earth carries within it a unique imprint. As the two neutron stars spiral closer together, the frequency and amplitude of the gravitational waves increase in a very specific pattern. By analyzing this chirp signal, scientists can determine the nature of the source and, crucially, infer the intrinsic strength of the gravitational waves, how much energy was actually released in the collision. This is analogous to knowing the true, intrinsic brightness of a standard candle. Then, by measuring the observed strength of the waves when they reach our detectors, how faint the chirp appears to us, scientists can calculate the distance to the event directly. It's a direct distance measurement, clean and simple, that completely sidesteps the entire chain of assumptions and calibrations needed for the traditional cosmic distance ladder. There is no interstellar dust to dim gravitational waves, no metallicity to worry about, no need to find and calibrate Cepheid variables. It is a pure measurement of how much spacetime has stretched between the event and us. The historic first demonstration of this technique came in August 2017 with the event known as GW 170817. The LIGO and Virgo gravitational wave observatories detected the characteristic chirp of two neutron stars merging. Just 2 seconds later, space-based and ground-based telescopes observed a corresponding flash of gamma rays, and then a slowly fading glow of light across other wavelengths, pinpointing the host galaxy. This was the full multi-messenger suite, The gravitational waves provided the direct distance to the collision, while the light from the afterglow provided the redshift of the host galaxy. By comparing this direct distance with the galaxy's recession velocity, astronomers could, for the first time, make a direct measurement of the Hubble constant that was completely independent of the traditional cosmic distance ladder. The result was a landmark moment, but it also perfectly encapsulated the current state of the field. The value they found was around 70, a number that sat squarely between the high local value and the low early universe value, with an uncertainty too large to definitively side with either camp. This is the current challenge and the immense promise of standard sirens. While GW 170817 was a spectacular proof of concept, a single event is not enough to resolve a discrepancy with the statistical significance of the Hubble tension. The uncertainty on the measurement from one merger is simply too great, like trying to determine the exact speed of a car by taking a single, slightly blurry photograph. To become the ultimate arbiter in this cosmic debate, we need a census of many such events. With each new neutron star merger detected, the uncertainty on the combined Hubble constant measurement shrinks. Current projections suggest that with a few dozen clean standard siren events, which the next generation of gravitational wave observatories should provide, we could measure the Hubble constant to within 1% precision or even better, a level of accuracy that could finally break the deadlock. The arrival of this independent judge is what makes the next decade so thrilling. If future standard sirens consistently converge on a value around 73, it would be a resounding validation of the local distance ladder and a definitive declaration that our standard model of cosmology is broken and needs new physics to explain the early universe's behavior. If instead they consistently point towards 67, it would suggest that the local measurement, for all its sophistication, does indeed harbor a hidden, cumulative systematic error that has so far eluded detection. Or they could land on a third, compromise value, forcing both camps to re-examine their assumptions. The power of standard sirens lies in their fundamental independence. They are built on the immutable laws of general relativity, offering a clean, direct readout of cosmic expansion that is untainted by the centuries-old astronomical methods that created the tension in the first place. They are the new, impartial witness being called to the stand, and their testimony has the potential to finally guide us toward the truth at the heart of this expanding universe. While gravitational waves offer a futuristic path to resolving the cosmic conflict, another powerful and remarkably elegant technique has been quietly gathering data for years, using a natural phenomenon that turns regions of space into incredibly precise cosmic lighthouses. This brings us to the 20th reason the Hubble tension is so multifaceted: the use of cosmic masers and megamasers. Imagine a naturally occurring laser, but instead of visible light, it amplifies microwave radiation. That's a maser, an acronym for microwave amplification by stimulated emission of radiation. In the cold, dense clouds of gas within regions of active star formation, water molecules can be energized, often by the intense radiation from a young star, causing them to emit a very pure, single-frequency microwave beam. It's a natural laser show playing out in the void, and for astronomers, these signals are far more than a cosmic curiosity. They are one of the most precise geometric tools we have for measuring the universe. The true power of this method is unleashed when we find these masers in a very special location, nestled in the accretion disk of a supermassive black hole at the heart of a distant galaxy. As vast clouds of gas and dust swirl at incredible speeds around the gravitational behemoth, the water molecules within them are stimulated to produce maser emission. From our vantage point millions of light years away, we don't see a single point of light. Instead, we observe a brilliant, pinpoint ring of maser spots orbiting the black hole. Using a global network of radio telescopes linked together in a technique called very long baseline interferometry, astronomers can map this ring of masers with stunning precision, resolving details smaller than a light year across from a distance of hundreds of millions of light years. This gives us an exquisitely detailed map of the black hole's immediate neighborhood, a map that comes with its own built-in cosmic speedometer. The methodology is a breathtaking application of pure geometry and dynamics. By tracking the motion of individual maser spots over time using Doppler shifts, scientists can determine the exact orbital speed of the gas in the disk. At the same time, the exquisite resolution of the radio telescope array allows them to measure the physical size of the maser ring directly on the sky. Here's the critical connection. If you know how fast something is moving in its orbit and you can also measure the physical radius of that orbit, you can directly calculate the distance to the system. It's a straightforward geometric distance, completely independent of the rungs on the cosmic distance ladder and the complexities of stellar physics that govern Cepheids and supernovae. There's no need to worry about interstellar dust dimming the signal as microwaves pass through dust clouds unimpeded. There are no questions about metallicity or the uniformity of explosions. This is a direct one-step measurement to a galaxy far, far away, making it one of the cleanest and most robust techniques in all of cosmology. This is the goal of the Megamesa Cosmology project, a dedicated effort that has been patiently observing these rare and precious systems. Each measurement is a monumental undertaking, requiring countless hours of telescope time and painstaking analysis to extract a single, precious distance to one galaxy. The results they have obtained are, therefore, incredibly valuable precisely because they come from such a fundamentally different process. And what have these pristine geometric measurements revealed? The answer is perhaps the most intriguing of all. The values for the Hubble constant derived from megamasers do not decisively side with either the high value from the local distance ladder or the low value from the cosmic microwave background. Instead, they have consistently landed in a fascinating middle ground, often hovering around a value of about 70 or 71 kilometers per second per megaparsec. This middle-of-the-road result adds a profound new layer of complexity to the entire debate. It suggests that the truth of the universe's expansion may not be a simple binary choice between two conflicting stories. Perhaps the local measurement, for all its sophistication, contains a small, residual systematic error that very slightly overestimates the expansion rate. Simultaneously, it could imply that the early universe model, while largely correct, is missing a subtle ingredient that causes it to very slightly underestimate the present-day expansion. The Megamesa results act as a sobering, independent referee, hinting that both major camps might be almost right, but that each is missing a small piece of the full picture. This geometric technique doesn't simplify the mystery, it deepens it, transforming a two-way argument into a three-body problem in cosmology. It tells us that the path to reconciliation may not be a dramatic revolution that overturns one entire method, but a delicate fine-tuning of our models and measurements, a painstaking process of finding the small corrections that will finally bring all the universe's clocks into synchrony. Amidst this landscape of gravitational waves and cosmic masers, another powerful and conceptually brilliant technique has been quietly adding its voice to the chorus, and it comes from looking at the very texture of starlight in distant galaxies. This leads us to the 21st pivotal reason the Hubble tension is so stubborn, the surface brightness fluctuation method, or SBF. Imagine you're looking at a vast, sprawling forest from a great distance. Up close, you can easily pick out individual trees, their trunks and branches distinct from one another. But as you move farther and farther away, the individual trees begin to blend together, and the entire forest starts to look like a smooth, uniform swath of green. The graininess of the forest disappears with distance, becoming smoother and more uniform the farther away you are. This exact same principle applies to the light from galaxies, and astronomers have learned to use this fading graininess as one of the most precise cosmic tape measures we possess. The method works by analyzing the light from a galaxy's halo, the vast, diffuse sphere of ancient stars that surrounds the bright central bulge and disk. This halo is made up of millions upon millions of individual, unresolved stars. When a galaxy is relatively close to us, our powerful telescopes can still perceive a subtle bumpiness in its light. Some pixels in the image will be slightly brighter because they happen to capture the light of a rare, bright giant star, while adjacent pixels will be slightly dimmer, sampling a patch of space dominated by fainter, more common stars. This pixel-to-pixel variation is the surface brightness fluctuation, the statistical graininess of the stellar population. The key insight is that this graininess has a known intrinsic scale. The average size of these fluctuations depends on the number and types of stars in the galaxy, which we understand quite well from stellar physics. Therefore, by measuring how smooth or how lumpy the galaxy's light appears to be from our vantage point, we can calculate the galaxy's distance. The smoother the light, the farther away the galaxy must be, because the individual stellar contributors have blended together into a more uniform glow. The extraordinary power of the SBF method lies in its independence and its precision. It doesn't rely on finding and studying individual stars like the Cepheid variable method. It doesn't require a cataclysmic stellar explosion like the supernova method. Instead, it uses the entire collective light of a galaxy's old stellar population as its ruler. This makes it immune to many of the systematic worries that plague other techniques. For instance, the pesky problem of interstellar dust is much less of a concern. While dust can dim the overall light of a galaxy, it tends to affect the entire image fairly uniformly. It doesn't selectively erase the subtle pixel-to-pixel fluctuations that are the heart of the SBF measurement. The method also bypasses the intense debates about stellar metallicity that complicate the Cepheid distance scale, because it is calibrated using nearby elliptical galaxies whose stellar populations are well understood. Now, here is where the SBF method delivers its crucial verdict on the Hubble tension. Several major studies, most notably those led by the Carnegie-Chicago Hubble program, have employed this technique to measure distances to massive elliptical galaxies that have also hosted Type Ia supernova. By using SBF to get a clean, geometric-like distance to these galaxies, they can directly calibrate the true peak brightness of the supernova that exploded within them. This creates a powerful, parallel distance ladder that completely bypasses the Cepheid variable stars. The results of this ambitious cross-check have been striking and consistent. The Hubble constant value derived from the SBF calibrated supernova does not point toward the lower, early universe value. Instead, it firmly and decisively supports the higher, local value of around 73 kilometers per second per megaparsec. It's as if a completely separate detective agency, using a different set of clues and a different analytical technique, has independently identified the same suspect. This is not a minor point, it is a profound reinforcement of the local measurements case. The significance of this agreement cannot be overstated. With each independent method that converges on the same high value for the Hubble constant, the possibility that the entire discrepancy is caused by a single, hidden systematic error in one technique grows increasingly unlikely. It would be a truly remarkable coincidence if the Cepheid distance ladder, the tip of the red giant branch method, and now the surface brightness fluctuation method, three entirely different approaches with different underlying physics and different potential pitfalls, all contain different, uncorrelated errors that just happen to push their final results in the exact same direction. The exact same number. The far more logical and compelling conclusion is that these methods are all correctly measuring the reality of our local cosmic expansion. The SBF method acts as a vital independent witness, its testimony strengthening the case that the tension is not an illusion born of observational error, but a genuine feature of our cosmos, a clear signal that the universe's present-day expansion rate is simply faster than our best models of its infancy can explain. And just when the debate seemed to be settling into a familiar stalemate, a brilliant new method emerged from the study of stellar life cycles, offering yet another independent path to measure the cosmos and delivering a verdict that further tightened the knot of the Hubble tension. This is the 22nd pivotal reason the problem is so inescapable: the timing of giant stars, specifically a moment of stellar brilliance known as the red giant branch tip. To understand its power, we need to step inside the final chapters of a star's life. Consider a star similar to our Sun, burning steadily for billions of years by fusing hydrogen into helium in its core. Eventually, that central fuel runs out. With the furnace at its heart extinguished, the core begins to contract under its own immense gravity, while the star's outer layers balloon outward in a dramatic response. The star transforms, cooling and swelling into a red giant, but for stars of a specific mass, the story doesn't end there. As the inert helium core continues to compress, it becomes hotter and denser until it reaches a truly cosmic flashpoint. At this critical moment, the temperature soars to 100 million degrees, and the entire core of helium ignites in a violent, explosive flash, a helium flash that occurs in a matter of seconds. This isn't an explosion that tears the star apart. Instead, it's a transformative internal detonation that fundamentally changes the star's structure and, crucially for astronomers, its brightness. This helium flash creates a spectacularly reliable cosmic landmark. At the precise instant the flash occurs, the star reaches its maximum luminosity on the red giant branch. It's a brilliant, predictable peak that acts like a stellar stop sign, marking the end of one phase of life and the beginning of another. For astronomers, this tip of the red giant branch, or TRGB, is a gift from stellar physics. Because the physics of this helium ignition is so universal, it always happens at the same core mass and temperature. The peak brightness these stars achieve is incredibly consistent. It doesn't depend on the star's age, its distance from the center of its galaxy, or many of the other factors that can complicate other stellar distance indicators. A red giant at the tip of the branch in our own Milky Way will have the same intrinsic brightness as one in a galaxy tens of millions of light years away. This makes the TRGB one of the cleanest and most powerful standard candles in the astronomer's toolkit, a brilliant beacon that shines with a known wattage across the universe. The methodology for using this stellar clock is both elegant and direct. Astronomers using powerful telescopes like the Hubble take deep images of a distant galaxy, capturing the light of hundreds of thousands of its stars. They then plot these stars on a color magnitude diagram, a kind of census that sorts stars by their color and their brightness. Amidst the scattered points representing stars in all stages of life, a distinct, sharp edge appears, the tip of the red giant branch. It stands out as a clear, horizontal line where the stars simply stop getting any brighter. By knowing the absolute, intrinsic magnitude of this tip from our calibration within the Milky Way, and then measuring how dim this apparent edge appears in the distant galaxy, scientists can calculate the galaxy's distance with remarkable precision, all in a single, decisive step. This bypasses the need for the multi-rung cosmic distance ladder and its associated complexities with Cepheid variables and their calibration. Now, here is where this beautiful stellar physics collides with the central cosmological mystery. Major observational campaigns, such as the Carnegie-Chicago Hubble program, have rigorously applied the TRGB method to galaxies that have also hosted Type Ia supernova. Their goal was to use this robust, one-step distance measurement to independently calibrate the true brightness of those supernova, building a parallel cosmic distance ladder free from the potential biases of the Cepheid-based approach. The results of this ambitious cross-check have been unequivocal and deeply significant. The Hubble constant value derived from the TRGB-calibrated supernova does not drift toward the lower, early universe values suggested by the cosmic microwave background. Instead, it firmly and consistently aligns with the higher value of around 73 kilometers per second per megaparsec found by the SH0ES team and other local measurements. It's as if a completely new witness, one who wasn't present for the earlier testimonies, has just taken the stand and corroborated the original story in exact detail. The convergence of the TRGB method with the other local techniques creates a formidable wall of evidence that is increasingly difficult to breach. It systematically eliminates a whole class of potential excuses for the tension. We can no longer plausibly suggest that the entire discrepancy is caused by some unknown error unique to Cepheid variable stars, because the TRGB method uses a completely different type of star and a different physical phenomenon. It would be an astounding coincidence if two entirely independent stellar distance indicators, each with their own distinct physics and potential systematic uncertainties, both contained hidden errors that just happened to push their final results in the exact same direction and by the exact same amount. The far more compelling and logical conclusion is that both methods are working correctly and are accurately measuring the true, faster expansion rate of our local universe. The red giant branch tip, a fleeting moment in the life of a common star, has become a crucial chronometer for the cosmos, its unwavering signal telling us that the problem is not in our stellar observations, but in our fundamental understanding of the universe's expansion history. Beyond the complex datasets and theoretical equations lies a deeper, more philosophical consequence of the Hubble tension, one that has sent ripples through the very soul of cosmology. This isn't just a puzzle about a number, it is a profound challenge to the scientific culture of the field itself. For the better part of 2 decades, the lambda cold dark matter model has reigned supreme, not just as a leading theory, but as the standard model of cosmology. Its predictive power has been so extraordinary, its agreement with so many disparate observations so seamless, that it achieved a status akin to a completed masterpiece. The Hubble tension is the single, stubborn crack in that masterpiece, and it has forced the entire community into a period of intense and necessary self-scrutiny. The question now being whispered in conferences and debated in journals is a fundamental one. Is it truly healthy for a scientific discipline to be so dominated by a single, overwhelmingly successful paradigm? On one hand, the existence of a robust standard model provides a powerful framework. It gives researchers a common language and a set of well-defined rules against which to test new ideas. It allows for incredible precision in planning missions and interpreting data, but there is a hidden danger in such success, a risk of intellectual complacency. When a model works so brilliantly, it can subtly discourage scientists from pursuing truly radical alternatives. The path of least resistance becomes one of incremental tweaks within the existing framework rather than daring leaps outside of it. The Hubble tension has shattered that comfort. It is the anomaly that cannot be ignored, the data point that refuses to be assimilated. In doing so, it has acted like a cosmic alarm clock, jolting cosmologists out of a dogmatic slumber and revitalizing the search for what lies beyond the established frontiers. It has rekindled a spirit of creative rebellion, encouraging theorists to dust off old, discarded ideas and dream up entirely new physics that just a few years ago might have been dismissed as too speculative. This crisis serves as a powerful, humbling reminder of a core principle of the scientific method. Our best theories are always provisional. They are maps of reality, not reality itself. Unlike any map, they are based on the data available at the time they were drawn. The Hubble tension is the universe showing us a vast, unexplored territory that our current map does not include. It forces us to confront the fact that our understanding, no matter how elegant and mathematically beautiful, is incomplete. This humility is not a sign of weakness, it is the engine of scientific progress. Every great revolution in physics, from the shift from a geocentric to a heliocentric solar system to the advent of general relativity, was born from an anomaly that the prevailing model could not explain. The Hubble tension is a gift in that sense, a clear, statistically undeniable signpost pointing toward the next great leap in our understanding. Ultimately, this is about more than just the rate of cosmic expansion. It's about our relationship with the cosmos. For a time, it seemed we were on the verge of a theory of everything, a complete and final description of the universe's history and fate. The Hubble tension has forcefully pulled us back from that precipice, reminding us that the universe is under no obligation to conform to our intellectual desires. It still holds profound, fundamental mysteries that defy our current comprehension. This isn't a failure of science, it is its greatest promise. The sense of awe and wonder that comes from staring up at a starry sky is mirrored by the awe a scientist feels when confronted with a deep, unsolved mystery. The Hubble tension guarantees that the golden age of cosmology is not behind us, but ahead of us, filled with the thrilling potential of discovery and the promise that the universe still has profound secrets left to reveal. Yet, with all the brilliant minds and sophisticated tools already focused on this problem, the most exciting chapter in the story of the Hubble tension may still be waiting to be written. This brings us to the 24th and perhaps most hopeful reason this cosmic mystery captivates us: the dawn of a new era of observation, where a fleet of next-generation telescopes and space missions stands poised to attack the problem with a power and precision that was unimaginable just a decade ago. These are not merely incremental improvements, they are revolutionary instruments designed to systematically hunt down and eliminate potential sources of error, offering our best chance yet to finally hear what the universe is trying to tell us. Leading this vanguard is the James Webb Space Telescope, a technological marvel that has already begun to transform our view of the cosmos. While its predecessor, the Hubble Space Telescope, has been the workhorse for building the local distance ladder, it faced a fundamental limitation. It observed primarily invisible and ultraviolet light, wavelengths that are notoriously vulnerable to dimming and reddening by interstellar dust. The Webb telescope, with its massive gold-coated mirror and suite of exquisitely sensitive infrared instruments, cuts through this obstacle like a warm knife through butter. Infrared light pierces through cosmic dust clouds with far greater ease, allowing Webb to observe the crucial Cepheid variable stars with a clarity Hubble could never achieve. More than just seeing them clearly, Webb can measure their pulsations and brightness in the infrared, where the confounding effects of dust extinction are minimized by a factor of nearly 10 compared to visible light. This means the Webb telescope is effectively remeasuring the entire cosmic distance ladder with a cleaner, sharper ruler. By observing the same Cepheids and supernova hosting galaxies that Hubble studied, but in the infrared, astronomers can perform a critical cross-check. If the high Hubble constant value persists even when the pesky variable of dust is almost entirely removed, it would be a monumental blow to the idea that interstellar grit is the culprit, strongly pointing instead toward a need for new physics. The first results from these observing campaigns are already trickling in, and the entire cosmological community is watching with bated breath. But the assault on the Hubble tension doesn't end with Webb. On the horizon, the Nancy Grace Roman Space Telescope promises to unleash a torrent of new data that will shift the search into a new statistical gear. Think of the current effort like a detective meticulously investigating a handful of key witnesses. The Roman telescope, with a field of view over 100 times larger than Hubble's, will be like deploying an entire army of detectives to interview thousands of witnesses simultaneously. Its primary mission includes a vast, high-resolution survey of the sky, during which it is expected to discover and meticulously measure thousands of new Type Ia supernovae. This enormous sample size is a game-changer. It will allow scientists to move beyond worrying about tiny, individual systematic errors and instead study the population of supernova as a whole. They will be able to see with overwhelming statistical force whether supernova in different types of galaxies or different cosmic environments have subtly different properties. This will finally settle the fierce debates about metallicity dependence and host galaxy effects. Does a supernova in an old, metal-poor galaxy truly have the same peak brightness as one in a young, metal-rich galaxy? With a dataset of thousands, Roman will give us a definitive answer, either solidifying our standard candles or providing the precise corrections we need to apply. Furthermore, by finding so many supernovae at greater distances, Roman will allow us to map the expansion history of the universe with a smooth, continuous detail we've never before possessed, directly probing whether the acceleration has changed over time. Meanwhile, the European Space Agency's Euclid satellite is approaching the problem from a completely different angle, focusing on the architecture of the dark universe. While Roman will excel at studying individual stellar explosions, Euclid is designed to map the geometry of the cosmos itself in 3 dimensions. Its primary goal is to trace the history of cosmic expansion and the growth of structure by observing billions of galaxies across 10 billion years of cosmic history. It will achieve this by measuring 2 key phenomena: weak gravitational lensing and baryon acoustic oscillations. Weak gravitational lensing involves detecting the tiny, subtle distortions in the shapes of distant galaxies caused by the gravitational pull of the dark matter that lies between them and us. This provides a direct measure of how matter is clustered throughout the universe. Simultaneously, Euclid will create the most precise map ever made of the baryon acoustic oscillation scale, that frozen sound wave imprint from the early universe, using it as a standard ruler across cosmic time. The combined power of these measurements from Euclid will deliver an independent, incredibly precise measurement of the Hubble constant, but more importantly, it will tightly constrain the properties of dark energy and dark matter. If the Hubble tension is caused by an unexpected behavior of dark energy, like a brief early burst or a slow evolution, Euclid's exquisite mapping of the cosmos's expansion and structure over billions of years is almost certain to find it. The true power of this new golden age of astronomy, however, will be realized when these observatories work in concert. Imagine a scenario where the James Webb Space Telescope provides a rock-solid, dust-free calibration of nearby supernova. The Roman Space Telescope discovers and tracks thousands of these explosions across a vast volume of the universe, and the Euclid satellite provides a simultaneous, independent measure of cosmic geometry and structure growth from the same patch of sky. This multi-pronged, multi-wavelength assault will create a cross-checking network of unprecedented robustness, a discrepancy that survives the combined scrutiny of Webb, Roman, and Euclid would be virtually unassailable. It would be the universe stating, in no uncertain terms, that our fundamental models require a profound revision. We are no longer just looking through a single keyhole, hoping for a glimpse of the truth. We are building an entire wall of windows, each offering a different, crystal-clear view, and together they will illuminate the deepest secrets of cosmic expansion. And this brings us to the final, and perhaps most profound, reason the Hubble tension captivates us so deeply. Beyond the satellite data, complex equations, and cosmic implications, this is ultimately a uniquely human puzzle. At its heart, the Hubble tension is not merely a conflict of numbers. It is a conflict of interpretations, of deeply held methodologies, and of distinct scientific cultures that have evolved around our 2 most powerful ways of seeing the cosmos. On one side, you have the cosmologists who study the early universe, whose work is rooted in the pristine, mathematical elegance of fundamental physics and the statistical power of all sky surveys. Theirs is a world of theoretical models and global parameters, where the universe is treated as a single, coherent system that can be understood from its initial conditions. On the other side, you have the astrophysicists who measure the local universe, whose craft is built on painstaking, empirical observation of individual stars and galaxies. Theirs is a world of meticulous calibration, of battling systematic errors, and of building a cosmic ladder one careful rung at a time. Both approaches are pillars of modern science, and both camps are filled with brilliant, dedicated people who are utterly convinced of the robustness of their own methods. The tension arises because these two pillars, which should be supporting the same edifice, are instead pushing in slightly different directions, forcing a fundamental conversation about what constitutes proof and where the truth actually lies. The human drama unfolding behind the scenes is what transforms this from a dry statistical discrepancy into a compelling story. Picture the late nights at research institutes where postdoctoral fellows stare at lines of code, running and rerunning their analyses, haunted by the possibility of a subtle bug that could explain everything. Imagine the intense atmosphere at major international conferences where senior scientists who are colleagues and friends engage in passionate public debates over a coffee break, each defending their data with a conviction born from years of painstaking work. There are the tense collaboration meetings where one group presents a new result that tightens their error bars, and the other group responds with a battery of pointed questions, searching for any potential weakness, any unaccounted for systematic effect. This isn't hostility, it is the essential, rigorous process of peer review playing out in real time. Every claimed discovery of a hidden bias is met with a flurry of activity, a re-examination of the data, and the development of ever more sophisticated cross-checks. The scientists involved are not just dispassionate calculators. They have invested a significant part of their professional lives into these measurements, and the stakes for their careers and for our understanding of the universe could not be higher. This dynamic struggle showcases science not as a static collection of facts in a textbook, but as a dynamic, messy, and gloriously human process of discovery. It is a living, breathing enterprise defined by curiosity, skepticism, and an unwavering commitment to finding the truth, no matter how inconvenient it may be. The Hubble tension is a powerful reminder that scientific progress is rarely a straight line. It is often a zigzag path filled with false leads, stubborn anomalies, and fierce debates. It is in these moments of profound disagreement that science is at its most vital and most honest. It forces everyone involved to question their assumptions, to refine their techniques, and to think more creatively than they ever have before. The very existence of this tension is a testament to the health of cosmology. It proves that the field is alive with critical thinking and that no theory, no matter how beautiful or successful, is safe from being challenged by new evidence. Ultimately, the story of the Hubble tension is a story about us. It's about our relentless drive to comprehend the vast cosmos we inhabit and our humble acknowledgement that our knowledge is always provisional. It highlights the incredible power of human ingenuity, from the engineers who built the Planck and Hubble telescopes to the theorists dreaming up wild new ideas like early dark energy. But it also underscores our limitations and the sheer difficulty of perceiving reality from our tiny vantage point in an unimaginably large and complex universe. Whether the final resolution comes from a revolutionary new particle, a deeper understanding of stellar physics, or something no one has yet conceived, the journey itself has been invaluable. It has sharpened our tools, expanded our imaginations, and brought the global scientific community together in a shared, epic quest. The Hubble tension is more than a problem to be solved. It is a privileged window into the very engine of scientific revolution, a reminder that the greatest mysteries are not just out there in the stars, but are also woven into the fabric of our own relentless pursuit of understanding. This journey through the many layers of the Hubble tension ultimately brings us to the final and most staggering consideration, the profound stakes for fundamental physics itself. We are not merely haggling over a digit in a cosmic speed limit. The resolution of this crisis will force us to answer one of the most profound questions we can ask. Is our current rulebook for the universe a collection of theories that has served us brilliantly for a century, fundamentally incomplete? The implications reach into the very bedrock of physical law, potentially rewriting our understanding of everything from the force of gravity to the nature of the vacuum of space. At the most revolutionary end of the spectrum lies the possibility that we must modify Einstein's theory of general relativity. For over 100 years, this theory has been the unchallenged king of cosmology, predicting everything from the bending of starlight to the existence of black holes with uncanny accuracy. Its equations underpin the entire lambda-cold dark matter model, governing how matter and energy shape the cosmos. To suggest a change to general relativity is to suggest altering the very language we use to describe gravity and spacetime. Yet the Hubble tension is forcing serious scientists to do just that. Perhaps on the largest cosmic scales, gravity behaves differently than we think. Maybe it leaks into extra dimensions or its strength evolves over time. Theorists are actively developing so-called modified gravity models, intricate new sets of rules that would keep all of general relativity's local successes, like correctly predicting the orbit of Mercury, while altering its behavior on the scale of the entire observable universe to account for the faster local expansion. If such a model were to succeed, it would represent a paradigm shift as monumental as the transition from Newton's gravity to Einstein's, redefining one of the fundamental forces of nature. Alternatively, the solution may not lie in tweaking gravity, but in deepening our understanding of the cosmos's mysterious contents. The Hubble tension could be the key that finally unlocks the true nature of dark energy. Our standard model treats it as a constant and immutable force inherent to empty space. But what if it's dynamic? Imagine a universe where dark energy is not a passive backdrop but an active, evolving field, sometimes called quintessence. This field could have been stronger in the past, providing that extra kick of expansion that would make the early universe's prediction align with our local measurement. Discovering that dark energy evolves would transform it from a simple cosmological constant into a complex physical entity with its own rich physics, a new cosmic fluid that changes the destiny of the universe. This wouldn't just solve the Hubble tension, it would answer the question of whether the universe's acceleration will continue forever, or if this repulsive force might one day fade away or even reverse, leading to a cosmic collapse. Then there is the humbling yet equally valid third path, the possibility that this entire grand crisis is built upon a foundation of subtle, compounded errors. After all, we are attempting to measure the entire universe from a single, infinitesimal point within it. The cosmic distance ladder is a human construction, a masterpiece of inference, but still vulnerable to the limits of our perception. Could there be a systematic error, perhaps in our understanding of how Cepheid variables pulsate in different galactic environments, or a tiny, unaccounted-for effect in the calibration of the Planck satellite's detectors that we have simply not yet discovered? If this is the case, and a decade from now the tension evaporates under the glare of better data from the James Webb and Roman telescopes, the outcome would be just as profound. It would be a breathtaking testament to the robustness of our standard model of cosmology, a triumphant validation that our current understanding, while incomplete in minor ways, is overwhelmingly correct. It would reinforce the pillars of 20th century physics and show that our methods, when pushed to their absolute limits, are capable of achieving near-perfect consistency. The story would be one of human ingenuity overcoming a monumental challenge, not by revolutionizing physics, but by perfecting our craft. This is why the Hubble tension is not just another item on the scientific to-do list. It is a fork in the road for fundamental physics, and the path we take will define the course of scientific inquiry for the next generation. A confirmation of new physics would unleash a golden age of theoretical and experimental work, as physicists rush to test predictions of modified gravity or dynamic dark energy. A resolution through systematic error would instead cement our current framework, allowing us to use it with even greater confidence to probe the remaining mysteries of dark matter and the universe's origin. In either case, the pursuit of this single number has become the defining scientific endeavor of our time, a concentrated effort to answer the biggest questions we can pose about the nature of reality, time, and the cosmos we call home. The stakes could not be higher, for the answer will not just tell us how fast the universe is expanding, but will reveal how much we have truly learned about the fundamental rules that govern everything. And so, after exploring this intricate tapestry of evidence and ideas, the true weight of the Hubble tension comes into full view. This is not a single puzzle with a single missing piece. It is a crisis woven from 25 distinct threads of perplexity, each one a reason why this single number defies a simple explanation. We have seen how it emerges from a clash between our two most trusted cosmic measuring tapes, each refined to an incredible precision yet pointing to different realities. We have grappled with the statistical certainty that this is no mere fluke, but a 5 sigma declaration that something is fundamentally amiss. The tension has persisted and even deepened as our tools have improved, surviving every attempt to explain it away with better data. It represents a direct challenge to the lambda cold dark matter model, our most successful cosmological framework, suggesting that the universe's evolution from its infancy to the present day did not follow the script we have written for it. We have delved into the vulnerabilities of the cosmic distance ladder, a multi-step construction where a tiny, hidden error in a Cepheid variable's calibration or a supernova's peak brightness could propagate into a significant bias. We have contrasted this with the early universe measurement, a value not directly observed but inferred through a complex model from the pristine snapshot of the cosmic microwave background, making the tension a potential failure of that very model. The problem is reinforced by independent verification, with multiple teams using different stars, Cepheids, red giants, and the tip of the red giant branch, all converging on the same high local value, while early universe probes like baryon acoustic oscillations sing in harmony with the CMB for a lower one. This multi-pronged conflict creates a direct crisis for the universe's age, threatening a logical absurdity where the oldest stars appear older than the cosmos itself. We have investigated potential astrophysical culprits, from the confounding dimming of interstellar dust to the possibility that we live in a vast cosmic void, a local underdensity where expansion runs faster than the cosmic average. We have considered how our own peculiar motion, pulled by gravitational giants like the Shapley supercluster, might be contaminating our view of the pure Hubble flow. The plot thickens with the realization that the Hubble constant is entangled with other cosmic parameters. Trying to force a solution by adjusting it creates new tensions in the clumpiness of matter, showing that our cosmological model is a delicately balanced mobile where moving one piece disrupts the entire structure. Then we journeyed into the realm of new physics, where ghostly neutrinos with slightly more mass, or even a hypothetical sterile neutrino, could have altered the early universe's expansion in a way that resolves the discrepancy. We encountered the elegant idea of early dark energy, a transient cosmic booster rocket that gave the young universe an extra push, changing the initial conditions from which we project forward to the present day. And we have looked to the future, where revolutionary tools, gravitational wave standard sirens, the infrared clarity of the James Webb Space Telescope, the vast statistical surveys of the Roman Space Telescope, and the dark universe mapping of Euclid are converging to attack the problem with unprecedented power. This is what cutting-edge science truly looks like. It is not a clean, linear path to truth. It is a messy, uncertain, and gloriously chaotic process, filled with passionate debates, dead ends, and moments of breathtaking insight. It is a human endeavor driven by curiosity and a stubborn refusal to accept inconsistency. The Hubble tension, in all its complexity, is a gift. It is the universe presenting us with a profound mystery, a clear sign that our current map of reality is incomplete. The resolution will not come easily. It might arrive as a whisper from a new particle detector, a flash of insight from a theorist's blackboard, or a stunning, unexpected dataset from a next-generation telescope. The greatest breakthroughs in science have always emerged from such stubborn anomalies, so stay curious, follow the news from these incredible observatories. The story is far from over. In fact, we are living through one of the most exciting chapters in the history of cosmology, and the next page could be turned at any moment, revealing a deeper, more wondrous understanding of the cosmos we call home.